I'm not a mathematician, and I work in a largely experimental group. So what I'm going to talk about is how we do photoacoustic tomography in practice and give you some of the reasons why, and maybe highlight where that differs slightly from the models that are used for developing reconstruction algorithms. So I'm going to have more questions possibly than answers. So I'm going to start off with a brief introduction. So Simon Arridge gave an introduction earlier on. I'll go into a little bit more depth in the physics from the basis, so that's more what I know about than the maths. I'll talk about some experimental setups, so not just the one we use at UCL, but ones that are used in various groups around the world, and you can see how they differ. And then a few areas in which the assumptions typically made in the reconstructions aren't necessarily exactly what we need experimentally. So these last three points. So what is the photoacoustic effect? Well, going right back to 1880, Alexander Graham Bell discovered the photoacoustic effect within a few months of the Curie brothers discovering piezoelectricity. So it's quite old. In fact, Bell thought it was going to be the main mechanism behind what was since become the telephone. He invented a photophone before he invented the telephone, and he thought it was going to take over the world. This was one of his early experiments. He had sunlight coming in through a window and reflecting off a mirror, and then he's got a chopper, like a fan basically, chopping the light, and then he's reflected it onto a bulb which has got some soot on it or some carbon black. And he's listening, and he found he could hear a frequency which corresponded to the blade passing frequency of the fan. So he deduced that acoustic waves were generated by the absorption of modulated electromagnetic radiation. Now, in photoacoustics, we normally just use pulses, a few nanoseconds long. Just on terminology, half the people doing photoacoustics call it photoacoustics, including our group. The other half call it optoacoustics. There's no difference whatsoever apart from the spelling. And thermoacoustics, certainly this part of the problem that I'm talking about, the acoustic part, for thermoacoustics where you have microwave excitation, it's the same. The quantitative part, the part that Simon talked about, that'll be different from microwaves because you wouldn't model them with the same models. And also, we're not talking about the acousto-optic effect, of course, which is where you can scatter light using sound waves. So why do people want to do photoacoustics? Well, I suppose the more basic question, why do people want to do optical imaging in tissue, clinically? And it's because there's a lot of chemical information available if you do it at multiple wavelengths. So that's the justification for looking at optics. Now, if we shine light into tissue, we find that very superficially it travels ballistically in straight lines. So you can do microscopy. And deeper than a few millimeters, the light's essentially diffuse. So you can do diffuse optical tomography. Now, these are two extremes in two senses, one in the depth you're reaching and also in the spatial resolution you're achieving. And photoacoustics fills in the gap in between. So you get around the fact that you're getting heavily scattered light by encoding the optical information onto an ultrasound wave, which is much less scattered. So you're retaining you're hoping that you can retain the wavelength, the information as a function of wavelength, but get out better spatial resolution. On the next slide, I just want to talk about something I'm not going to talk about, if you see what I mean. So a lot of the literature, certainly in the last few years, has been about, in photoacoustic imaging, has been about microscopy rather than tomography. So there's a couple of different systems that have been worked on a lot, in particular by Li Hong Wang's group. He's the sort of king of photoacoustics experimentally. And they're called acoustic resolution microscopy, photoacoustic microscopy, and optical resolution. So here, what they're doing is they're looking at quite superficial depths, less than a millimeter. And they focus, in this case, they're focusing their detector to a point or to a line, really. And then they just scan this acoustic detector across the surface. So they're not doing any reconstruction. They're not doing any maths. With optical resolution, it's even shallower depths they're looking at. And here they focus their light. So you only get a photoacoustic signal at a optical diffraction limited spot. So they can get images down to less than a micron. Okay, but what we're talking about, and this is a slide Simon put up, but I won't apologise for putting it up again. We're talking about tomography. So here we flood the tissue with light. It gets absorbed in some places, and in the places it gets absorbed, you get a generation of a sound wave generated, and it travels to the surface. In the system we've got at UCL, we have a transparent detector array, which is why we've drawn it like this. And this is the part of the problem that Simon talked about. So this is all optical. Light's coming in, you get a distribution of light fluence, some of that's absorbed, and you get this absorbed energy density. Now to connect it to the acoustic part of the problem, which I'm going to talk about in this talk, you need this additional parameter. It's often called the Guneisen parameter. I try and call it the photoacoustic efficiency. It's not, a Guneisen parameter is a specific thermodynamic constant for a particular material, and if your absorber was in a material with exactly the same thermodynamic properties and it didn't fluoresce, this proportionality constant would indeed be the Guneisen parameter. But if you, for example, your absorber slightly fluoresced, some of the energy would be lost into fluorescence. Or let's say a lot of work's recently been done on using contrast agents for photoacoustics. So if you had a gold nanoparticle in a fluid background, let's say water background, and the gold nanoparticle absorbed, what you would get there is that the important parameter wouldn't be a Guneisen parameter, it would be the rate at which the heat could escape from the gold nanoparticle into the surrounding fluid. So more important would be things like the thermal interfacial resistance of the particle. Okay, that's an aside. We've got some constant of a proportionality. We've also got another condition which we assume when we're building the model for this, which is that the optical energy is delivered, all of it is delivered, before anything in the tissue started to move. So the light comes in and scatters around, and that all happens and gets absorbed. That all happens in maybe some few nanoseconds. So the pulses are typically 5 nanoseconds. So maybe after about that sort of time, all the light that's going to be absorbed has been absorbed, and we assume that the tissue hasn't had time to mechanically move. So that's why you get an increase in pressure, in particular, because there's no change in the density. So we make this assumption that the initial particle velocity is 0, or if we're talking about pressure, the rate of change of the pressure is 0. Okay. So these are the forward problems we have in photoacoustics. We start off with some optical coefficients. We've got light propagation, and we end up with initial acoustic pressure distribution. This is what we're going to try and image. The waves travel down. We make some acoustic measurements. We solve the acoustic inverse problem, and that's what I'm going to talk about this. And Simon talked about this, solving this optical inverse problem to recover the optical coefficients. Now, clearly, if you want to do the quantitative problem, you need to get a pretty good image in the first case. And and you want to get a quantitatively accurate estimate of your pressure. Rather than use the wave equation, we actually model it with the first order equations, which would give you the wave equation, mostly for pragmatic reasons. So we normally use these acoustic equations for acoustic pressure, acoustic particle velocity, and acoustic density. You could combine these to get a wave equation. The reason we use them is because in our work in ultrasound imaging, we've extended these with nonlinear terms and absorbing terms. So for photoacoustics, which is acoustically linear, the acoustic pressure amplitudes are very small, we use these, and we put them in a very standard, fairly standard time-stepping Fourier collocation pseudospectral method. Okay, so we just timed it round. So the simulations and indeed the reconstructions I'm going to show of real data in this talk were done with this model, and here's a little example of it at work, which I know some of you have seen more than once before. So here's our initial value problem that we're solving, and we've got some initial pressure distribution, and we've got some measurement surface. So we have to remember that in most reconstruction algorithms, it's assumed that this is not a boundary. This is just a place on which you measure. The waves travel through it. So the waves will travel out through it, and at each point you measure an acoustic time series So in practice, of course, this is discretized into some finite number of points. And then one way you can reconstruct, which is one of my favorites, and it's also the best fitting movies, is use time reversal. So you know all the data on this boundary, and if you've waited long enough that there's nothing inside the domain, you can reconstruct the field at every previous time, in particular, the initial time. You can reconstruct it from these boundary measurements by sort of playing it back in, if you like. And the condition that the field becomes zero, sometimes called the Huygens condition, is actually not essential to have satisfied. Stefanov and Ullman showed a few years ago that as long as you wait long enough that the waves have had time to travel half the biggest distance across here, then you can still use time reversal. What you do is when you start off the reconstruction, you don't start off with zero. You take your final time points and you calculate the harmonic extension from those time points into the domain, and use that as your starting point. And you can iteratively form a Neumann series which will converge to the right solution. So I'll come back to that later actually as well. Okay, so there's lots of algorithms in the literature, and I'm not going to try and talk about them. There's some excellent reviews if you want to learn more by Peter Kuchman and Leonid Kunyansky, but they often assume a certain detection geometry. So the early ones were spherical surfaces, infinite cylindrical surfaces, infinite planes. This is supposed to represent sides of a cube. But the key thing is that they're all closed surfaces. And there's various different types of solution as well. So you've got filtered back projection types, lots and lots of them, all exact if you've got noise-free data and you've got a complete data set. Series solutions, some of which can be very fast because they use FFTs. Time reversal, which I just showed. But a key point is that most of them assume free space propagation. So I'm going to question, well, both of these assumptions are not necessarily helpful in practice. A key condition, which is separate from any particular reconstruction, is this idea of this visibility condition. So if you want to reconstruct a target exactly, it needs to be in a visible region. So every point in the target, it has to have normals to it, have to go through the measurement surface at some point. So we wouldn't be able to reconstruct this edge or these edges in these cases if this was our detectors, but we would be able to reconstruct something if it sits in the middle. So bearing that in mind, that you need this visibility condition if you want to get any sort of exact image. I'll just show some of the systems that are used in practice for this experimentally. This was one of the first systems, and certainly a groundbreaking paper from Li Hong Wang's group in the States. They're measuring with a transducer which is focused in the plane. So they're restricting themselves essentially to two-dimensional photoacoustics. And they illuminate diffusely from above, and then they rotate the transducer around the head of the rat or the mouse to recover their data. Here's a similar idea from the group in Munich in Germany. This is what they're trying to image, and again they're imaging a slice of it. Now here they're focusing their acoustic detection in the plane, and also focusing to some extent as best they can with a diffuse medium. They're focusing their light in the plane as well. And again, they rotate, it looks like in this example, they actually rotate the sample. This is a cartoon of a system we use at UCL. So here we measure over, this is the detecting region, just a small piece of a plane. And I'll come back to this system later, but we measure points on this. This is an array, essentially, a planar array. Another example of a planar array, which more and more people are trying, is to use a clinical ultrasound system, or certainly transducers, linear array transducers of a similar type, and just sort of strap a couple of optical fibers on them to generate some light. So they're trying to reconstruct, again, from planar data, limited aperture planar data. Bob Kruger built the system which he's used for breast imaging and small animal imaging. And here he does have a visible region, in so much as he's essentially got a hemispherical detector. And so objects inside this, you could in principle recover exactly. These are the positions of his acoustic elements, acoustic detection elements, and he simulates more of these by by rotating this transducer array by a number of positions. So he gets quite a lot of measurement positions. And one example, which perhaps one of the few where they have close to a total set of measurements, is this example here, and where they've got here's the target, here's the mouse hanging up in here. These things are fiber bundles delivering the light, and this is the acoustic detection array, and this stays still, and the detector array and the fiber bundles will rotate round. So this gives them acoustic detection all the way around. It's a problem for the quantitative reconstruction in that every measurement they make here, their light sources in their different position. Okay, so if we go back to, let's say, this example here, where Bob's got quite nice data, but how does he reconstruct an image if all the reconstruction algorithms assume you've got a complete field of view? So you should be able to get an exact algorithm. Actually, you can fairly straightforwardly get the exact solution in the limited view case, as long as you've got a visible region, just by iterating. So if we have a forward operator A and an imaging operator, I've called it T because of time reversal. If you've got full data, they're just going to be inverses. If you haven't got full data, there's going to be some error. So we've got this error operator, and you can write a Neumann series which will converge in the visible region. Why does it converge? The way I think about it is that here's the iteration you'd actually do. So you'd take your previous image, forward propagate it with your acoustic model, look at the difference between that and the measurements you had, and image the difference. And you keep doing that. And the way I think about why it works is because you're imposing two conditions of prior knowledge, I suppose. One is this zero particle velocity condition I talked about before. So time reversal when you're imaging doesn't assume anything about the particle velocity. You could get back to t equals 0 and have a different particle velocity if you started off with a different one. But by imposing the zero particle velocity in your acoustic forward model, you can, and also we also know that the image must be non-negative. Well, it's an image of energy essentially. It can't have any negative values. So if there are any negative values, we just throw them away, and by doing these two steps, you can get to the right answer. So just a little numerical example, if this was your measurement surfaces, and here's your thing you're trying to image, the acoustic waves travel out, and you time reverse them back in. Now, the first thing we notice is the amplitude is quite wrong. It's out by about a factor of 2 because you're only measuring half the surface, and you can see all these streaky artifacts. If you iterate it as above, it starts to converge to the exact answer in this visible region. You still have artifacts outside, but it still seems to be stable outside. Yeah.
So the non-negativity is a projection operator, or it's actually a reparameterization that you put there?
I don't know. I just throw away anything that's negative in the image.
Okay, so it's a threshold or a projection.
Yeah, thresholding this thing. Yeah. Okay, so my first question is whether you can do this non-iteratively. So we know that you should be able to get an exact answer in a visible region. Can we get away from having to use this iterative algorithm, because having to run the forward and reconstruction algorithm several times is quite slow. So that's my first question, and I don't know the answer. Okay, now what if you don't have a visible region? So I showed a couple of examples where we use here, for example, use a planar detection array. Why would we choose a planar detection array, which seems like a complete disaster, because there's no visible region at all, so you're never going to get the exact answer. So I just wanted to explain why, in practice, we do it. Photoacoustic signals are weak, so that's one thing to remember. They're quite weak, so you need good sensitivity. I'll come back to that point in a minute. You also often have a situation where you just can't get all the way around the object. So if you're imaging something on the skin or something on here or something, you're not allowed to dig in. Right? So you're restricted to a planar geometry anyway, so it's a practical reason. There are fast algorithms available for planar cases, so that shouldn't be underemphasized for experimentalists. If you can get an image quickly, that's important. But going back to this point here, if you photoacoustic signals are very broadband, so they've got very high frequencies in, and most of the reconstruction algorithms assume you've got point detectors. So if you want point detectors at very high frequencies, they need to be very small. If you get piezoelectric transducer elements, their sensitivity is dependent on their area. So if you make them very, very small, I mean, we're talking 20 microns or something, you won't be able to detect anything because the photoacoustic signal is too weak. So we use optical detection to get our measurements. I'm going to have a slide on that later on, but the point is that the optical detection is much easier to do if you've got a plane. So if you try and do optical detection over some arbitrary or curved surface, experimentally it becomes a nightmare. So there's various reasons why we've chosen a plane. Okay. Now, if you've got a planar geometry, there's going to be parts of your image that are sort of vertical, if you like, are not going to recover the edges for this because of this visibility region. And just as an aside, I was at a conference last week, experimental conference mostly, and there were two ingenious ideas that people came up with for overcoming this problem. And one was to, so here's our initial pressure that we're trying to get. We're not going to be able to recover edges because they don't have any edges parallel to the detector. So you just make some parallel to the detector, and they've done it in two ways. One was to change the Gruneisen parameter so that it made the image have some edges. So what they did is they focused an ultrasound detector at spots, essentially, lots of spots all the way down one after the other. And the Gruneisen coefficient's temperature dependent, so you've got a slight increase in the photoacoustic image there. So you could bit by bit recover things that you couldn't see if you did one shot. And the second one was to change the fluence, and so use lots of speckly images. So you'll use illumination that's speckly, so that it gives a speckly P0, and do that with lots of different speckly illuminations. Now that will only work very superficially, because if you go into the diffuse region, you lose the speckliness. But anyway, they're quite nice ideas, but they were experimental. I'll come on to what we might be able to try numerically in a minute. But first of all, given that planar detection seems like a complete disaster, let's look at some images that we get. So here's our array. This is the actual array. That little rectangle is a sensitive part. Here's a client lying on the scanner. He's got a tumor on his back. Simon showed an image earlier. Here's some other images that we get. These are images being used by people doing cancer research to look at how certain drugs disrupt vascular growth during cancer. But you can see these vessels quite nicely formed. And I've got one more. There we go. This is a mouse embryo. This one's actually outside the womb, but you can take these through the wall of the womb, so you can take them in utero. And you can see lots of details that I don't know what they are, but they're useful to the people studying the embryology. Now these images look quite good. They're all slightly cheating in that they're all showing maximum intensity projections of their 3D data set. If we look at actual slices of an image, so here's a simpler image, just some blood-filled tubes. And this is lying on our sensor, so if you like, in the plane here is our sensor sitting on top of the sensor, and I've reconstructed the data, and I'm just going to fly through it over here, and you'll see the vessels appear, and then after the vessels have gone, you see the sort of train tracks. So those are the train tracks of the limited aperture effect artifacts, which you lose quite a lot of them when you do a maximum intensity projection. But in the actual data, they're pretty obvious. So if you wanted to do some quantitative imaging, if you wanted to have this as the first step for your optical inversion, it would be a disaster because it's got loads of features that you don't want. So, given my sort of engineering training, we can do stuff to deal with these artifacts. It's not necessarily a beautiful thing, but we can smooth them away to some extent. So we applied the same iteration that I talked about before when you've got a visible region to get it exactly, right? We haven't got a visible region, but hopefully incorporating that prior data is going to help improve the image. And then we've stuck on another term just to sort of control the noise and, well, it's slightly edge preserving. Okay, so it's fairly standard techniques, and it helps. So if we look at, this is a slice through that previous fly-through data set. We can see some of these limited aperture problems coming up here, and they're going away here. What you can't see is the amplitude on these. If I plot a slice through here, this is the original one, which is a black line here, and this is the reconstructed one after iteration, which is the red line. So we've recovered what we expect to be close to the real amplitude, and importantly, actually, we've also improved the spatial resolution. I'm not entirely sure why, but we have. So it was 200 microns. We know the vessel was about 100 microns, the blood-filled tube, which is about what we recover. So it's an ad hoc technique, but it does help in practice. Okay. Are there ways we can use planar arrays? Are there things we can do to them to make them better? One thing we've wondered about is whether we can use reflectors. So we still want to use a planar array because the optics is good and we've got the system and so on. Can we stick a reflecting wall in? Now, if you did it in this case, you'd have, if you like, had your image there, you'd have an image source over here. So you could reconstruct by just mirroring the data and reconstruct, and it would be better. There was a paper last year by some guys in Li Hongwan's group where they did it with a reflector at 45 degrees. So they'll have a reflected image up here. So any features that aren't recovered by this plane are recovered by, if you like, the image detector, if you like, up here. So that helped them recover the images. A little while ago, we wondered about whether you could, if you had two walls either side of your planar array, so you had infinitely periodic image sources going either side, and it turned out you can reconstruct that quite easily because by using an FFT, which itself assumes periodicity in this dimension. So you can match the periodicity of the experiment with the reconstruction. Something we haven't tried, but we thought it might be useful to try if we knew how to reconstruct with it, would be to take like a bowl, and you could put your target, your mouse or something in here, and you could put your array like a lid, and then you could reconstruct from that, and you'd collect all the data. When wondering how far you could push this, we looked at whether you could. So from this idea that arrays are expensive but time is cheap, can you reconstruct from a single point? So if we had a single detector in the corner of a cavity, could we reconstruct from that? Well, it turns out you can't. You need all your modes to have separate modal frequencies. The only way you're going to associate a single time series with any spatial information is if each of your frequencies you detect can be related to a different eigenfunction in here. So you need some sort of chaotic cavity to do that. And of course, in practice, you're going to suffer from all sorts of problems of noise and the fact that you need to measure for a very, very long time. Konyansky looked at this question of whether you could, if you've got a reflecting box. So in this case, these sensors also reflect. We've got to remember, these arrays are solid things. So you've got a reflecting box, two sides of which, or in the 3D case, three sides of which, will be made of actual arrays. Can you reconstruct in this case? And he showed that you can. Essentially, you reconstruct, if you like, half the wave numbers from this sensor and half the wave numbers from this sensor, so you can get all directions. So you can get an exact image. And what about if you've got a box made of these arrays? Can you reconstruct from that? Well, there's two questions here. One is if your arrays are completely reflecting, can you reconstruct? Another one is if they're partially reflecting, so you have some sort of energy decay inside, can you reconstruct? I think in this case, Stefanov and Ullmann's algorithm, the time reversal algorithm I mentioned before, can be applied in either case. But in this case, if these walls or these walls are partially reflecting, so in other words, the reflection coefficients maybe half or something, then we don't have a solution. but it feels like you should be able to find one. So another question is, can you get exact reconstructions in this case here? Okay, I'm aware of the time, so I'll move on to another thing in reconstructions is that we need to know something about the medium properties. If we're going to reconstruct, we need to know how fast the waves have travelled out. So we need to know the sound speed. And of course, we don't know the sound speed. We know roughly the sound speed. In tissue, it's roughly 15, 14 meters per second. But it's not exactly that. And can we get it in some way? Now, if you've got full view data, you can recover the sound speed if you know it's uniform. Because you do your time reversal and you do it lots of different speeds. And the one which gives you an initial particle velocity of 0 is the right one. In practice, when we don't have full view data, we do a similar thing with just an image sharpness metric. So we just reconstruct with lots of different sound speeds in roughly the right region and pick the one that gives a nice sharp image. So that doesn't seem entirely satisfactory, but that's all we can do. It's been suggested that it might be possible to recover a heterogeneous sound speed. So you're imaging something where the sound speed varies with the different tissues. Recover it simultaneously with the photoacoustic data. And from what I've read, the closest anyone's come was a paper last year, but unfortunately it required the particle velocity Laplacian to be non-zero, which of course is not true in our case. So that seems an open problem still. In practice, you could use some sort of transmission ultrasound, a separate modality, to measure the sound speed, and that's been done. And then there's some algorithms, for example, that Ullman time reversal, which you can use to reconstruct. I should say people don't really do that very much in practice, but I have seen some toy experimental demonstrations. A perhaps harder question is, what if you've got, rather than, we've always assumed so far in this whole talk that everything's traveling in fluids, which for soft tissue is not too bad, because the shear waves in soft tissue travel extremely slowly, maybe 5 meters per second or something. But if you've got a bony region in the way, like if you're trying to do transcranial imaging, which has been tried, then should we take the fact that it's actually elastic into account? Now, if we want to do that, we kind of got to go right back to the beginning. I've only seen one paper on this a couple of years ago. We needed to complete reformulation of the problem because we now have equations for elastic waves. So that's something that would be useful to see some work on. Acoustic absorption. So acoustic absorption increases hugely as you go to higher acoustic frequencies. So by taking it into account, it's possible to recover some sharper features in your image. Of course, you need to regularize when you do that. There's a number of papers on this. The method that we use is by using this equation here and using it in time reversal. The particular form of this I won't have time to go into, but essentially we assume that the acoustic absorption follows a power law, and these operators will give you that power law absorption. Well, this gives you the absorption, this gives you the dispersion, the variation of the sound speed, which comes with absorption. And the point of writing this fractional derivative as a spatial derivative rather than the time derivative is a practical one of computation. You don't have to store previous time steps in your computation to apply it. It's extremely computationally efficient. That's not the only way to do it. Okay. Another thing which, if we're aiming for trying to get a quantitative estimate of our initial pressure distribution to feed up into the optical problem, something else we need to take into account is the fact that the density, the ambient density of the tissue will vary. There's some literature suggesting that it's roughly proportional to the sound speed in tissue, empirically. And so a reconstruction algorithm which would take that into account if we knew it would be interesting. Okay, my last point, coming back to why do we do optical detection? We do optical detection because we feel like we should use point sources, and we feel like we should have omnidirectional detectors to do our imaging with. And the question is just whether or not that's necessary. So all the image reconstruction algorithms assume that you're measuring at a point and waves coming from any direction are equally detected, equally sensitive to every direction. But do we actually need that? I mean, if we could use larger piezoelectric arrays, we could gain sensitivity. I mean, to normal incidents, you'd still measure the very high frequencies, but you just wouldn't measure the frequencies as an angle. So it would be, if you like, you'd have a sort of cone of acceptance angles where the waves would come in. So the question is, how would that affect? Well, two things. How would that affect the visibility? How would we want to build our arrays if we had large, sensitive elements, but that were directional? And secondly, would it be possible to do a reconstruction? My first thought was that this is just going to be like a limited view type problem. It just means you're going to lose data. But then a second thought was, well, if your directionality was so severe that it gave you one-dimensional data, it was measuring in just a line. So if you had your cone of acceptable angles got so thin that you're essentially only sensing waves coming in this direction, then you no longer need to back project over a whole domain. You just back project up a line. So you would have solved the limited view problem because you wouldn't have one. You just back project up lines. So it feels like maybe if we restricted the acceptance angle of our data, it might be a useful thing to do. Okay, so there's been a lot of progress on photoacoustics and the maths of photoacoustics over the last 10 years or so. And there's a lot of image reconstruction algorithm that's been done. They're still coming out of increased generality. But I've just spent half an hour just explaining what we actually do in practice in the hope that it might excite some people into putting some of the more practical aspects that we have to deal with into the reconstruction algorithms. And there's lots of people to thank. So thank you very much.
Thank you. Questions, please? I think people will be thinking about the questions here.
Excellent.
We pause.
I hope so.
Thank you very much.
Okay.